So now let's focus on the concept of the derivative. Okay, so in the last video, I showed kind of what we mean by the derivative in terms of the slope of a function at any point. So if we take the function f of x equals x squared, then the challenge here is finding, okay, what is the slope at this point or this point, right? So we can't really do that too well using any techniques that we already have, right? I think that a good illustration of this is using velocity and position, and the difference between average velocity and instantaneous velocity. So let's look at a related function just to kind of illustrate what we mean here. So here is a function that I have from a problem of dropping, really it's just throwing a rock out of a window. Okay. So I won't write out the whole problem because we're not really looking at solving the problem yet, but the problem basically says that a rock is dropped from a window of 64 at a height of 64 feet. It's determined that its height above the ground t seconds later is given by this formula. Okay, so if we won't look at exactly what the graph of this function would be, but we can kind of imagine what it would be, right? If it's dropped out of a window of height 64 feet, then that means that's like the y-intercept. And it says that it was dropped. So we assume that this is like the highest point, right? And that it just keeps going downwards from there. And if you remember about the quadratic functions, that would also make sense, right? This is basically the x squared function with a negative in front of it, so it opens downwards, and it's a vertical transformation 64 upwards. So it'll look something like this. So you can draw the entire function, but the function really only makes sense within this first quadrant. So sometimes what we might do is kind of extend it with a dotted line, even though this part doesn't really make physical sense in the context of this problem. Because in this problem, this would be the window, and this would be the ground. Okay. So there's lots of questions we can answer with this. Like we could answer, for example, when is it going to hit the ground? And that's more of an algebra question, not really using any calculus. One thing we might want to find is what we call its average rate of change. Okay. In this context, because S of t gives the position of the rock after t seconds. Okay. So the rate of change here, in other words, the rate of change in position, is what we would call velocity, right? So velocity, this is telling you how fast the object is moving, right? So it's the rate of change in position. We would measure velocity. This one is given in feet, and t is in seconds. So velocity would be in feet per second, right? So in other words, you're looking where we have some quantity in feet divided by some quantity in seconds. Okay. So if we wanted to know the velocity between 0 and 1, for example. So if we look at 1, first of all, where is this function at 1? So let's do s of 1. S of 1 is negative 16 plus 64. So it's going to be 48. Okay. So this point is at 148. And this point, of course, is at 0, 64. So if we want to know the average velocity, the average rate of change between 0 and 1, in other words, we're looking at, on average, how fast is it moving between 0 and 1 second, we would find the slope between those 2 points, right? That would give us the average rate of change. So the slope between those points, let me do it right over here, would be s of 1 minus s of 0 over 1 minus 0, which is going to be 48 minus 64 over 1, okay, which is going to be negative 16. And again, the top is in feet, the bottom is in seconds, so this is going to be feet per second. Okay. So the negative here tells us it's going down, right? So velocity is essentially speed with direction. So the direction in this case is the negative or positive sign. So negative velocity tells us that the position is going to be going down, decreasing. So this tells us that on average between 0 and 1, it was decreasing by 16 feet per second, right? Which makes sense because we're only moving 1 unit and we're going down exactly 16 feet, right? But we can do this with any 2 points. So what we're essentially doing here, and when I say essentially, I mean exactly what we're doing, is we're finding the slope of what we call the secant line between these 2 points. So this is called the secant line, okay? And the secant line is just a word for the line that goes through 2 points, okay? So we're not, we don't have to draw it if we use the formula, but that's essentially what we're doing. We're looking at the line that goes between those 2 points and we're finding the slope of that line. So again, on a line, the slope is going to be the same at any point, right? So this is how we would find the average velocity between 2 points. And we just need algebra to find this. But now what if we want to find the instantaneous rate of change at a point? In other words, what if we want to know how fast is this object going at 1? And only at 1, not between 2 points, but just at 1, right? If you're driving in a car, your speedometer tells you how fast you're going exactly at that point, right? It's not telling you how fast you went on average between 2 points. It's telling you, okay, at this point right now, this is how fast you were going. The instantaneous speed in that case, right? And velocity just gives us the direction. So how do we tackle that problem? What if we want to know exactly how fast is this going at 1? So, and notice we can kind of get a hint of it. If we think about the instantaneous rate of change at 0, well, it should be 0, right? Because at that point, the object's not moving, right? It's about to be dropped out of the window. So let's just take a look at a diagram here. Okay, so if you weren't in Math Tools 1, this is a program that I like to use a lot called Desmos, Desmos. Just the website desmos.com. So it's just an online graphing calculator. But if you click in the upper left corner, they have all these different complicated graphs you can make. So this is the one that they have built in for a secant line. Okay, so let's look at the secant line, and this is the function x squared. Maybe I could go ahead and change this to our problem here. Negative 16x squared plus 64. Okay, so we're going to need to scroll way up. but that is no problem. And I'll bring this point with us. Okay. So it's a little bit harder to see because the scale is so large here, but let me bring this inwards. You can see it's kind of sensitive here. So this is our problem. Okay, so what if we have this secant line between 2 points, right? So this is the point right here. It looks like this is about 1/4. It's, again, a little hard to see on this large of a scale. But what if we want to know the velocity at 0, just as an example? Okay, so what if we want to know exactly how fast it's moving at 0? And like I said, it should be about 0. So right here, this point right here is giving you the slope of the secant line. Okay. And you can see how they're calculating the slope here. And we'll go over exactly what these quantities mean in future videos, because this is kind of how we calculate the derivative. So you can see as I move it in, the slope is getting smaller and smaller, right? Okay. So when I get them really close together, the slope is getting very small. And as I move it in, it only lets me do so much of an increment here. But you can see that the slope is negative 0.96. That's as far as it'll let me go. And then if I keep moving in, it gets undefined, right? So why would I even care about doing this necessarily? Okay. Well, the slope at a particular point can be found by what's called the slope of the tangent line at that point. So the tangent line is a line that intersects the function at that point and only at that point. Okay. So in this case, if I had a function that looks kind of like this, and it only intersects just at that point, that would be what's called the tangent line. Okay. At this point, in this function, it's actually very easy to find. The tangent line, because it's perfectly flat right there, the tangent line is the line y equals 64. And you can test it. These functions will intersect at this point and only at this point. How do you find the intersection between 2 points? Well, or 2 functions, I should say. You can just set them equal to each other and solve. Where does this function, 64, equal the other function, negative 16t squared plus 64? Okay, subtract 64 from both sides. Divide both sides by 16. T squared equals 0 implies t equals 0. So the only place that they intersect is at t equals 0. So they only intersect at this one point. Okay. But this was just kind of a hunch based on the fact that it's getting flat right here. What if we want to look at the point 1? How do we find a tangent line at that point? Well, one thing we can do is kind of what we would do for limits. Okay. What if we found the average rate of change, which I'll abbreviate as AROC, between 1 and a point really close to 1, maybe like 1.01. Okay. So we'd find S of 1.01 minus S of 1 over 1.01 minus 1. Okay. So let's go ahead. I'll put this in the calculator. Okay. So this is what we end up with here. So we end up with negative 32.16 feet per second. So maybe you can keep plugging in numbers that are closer and closer to 1, and you can kind of see where this function is going. In other words, you can look at what the limit of this would be. So how exactly do we write that limit? Well, what we're really doing is we're finding these. All right, let's say we're finding s of 1 minus s of, I guess we're kind of doing it the other way. It doesn't really matter which way we formalize it, but let's say we're doing s of 1 plus h minus s of 1 divided by 1 plus h minus 1. Okay, so h here is just some small number, right? We're just looking at numbers that are just a little bit to the right of 1. And we're looking at the limit as h goes to 0, right? And this is a little difficult to find here maybe, because if we simplify this just a little bit, particularly on the bottom, you can see that it's just h. All right. So if we just plug in the limit as h goes to 0 directly, we get 0 over 0. So we get an indeterminate form, and then we have to tackle that more. So this is kind of the idea of a derivative. We want to find the slope of the tangent line at that point. And to find that function, what we do is we keep decreasing the width of those secant lines. In other words, we're finding the secant line between 2 points, and we keep bringing those 2 points closer and closer together, right? And then to get them perfectly on top of each other, we take the limit as their width, as the distance between those points goes to 0, and that gives us what is called the derivative. So we'll explore this a little further in the next few videos.